In this video, we're going to discuss the solutions for the final exam on linear algebra from spring semester 2018. Exam contains the two parts. The first part contains 4 technical questions and the second part contains 4 problems on the following topics. Let's go through the questions of the first part. In the first question, we are given 2 vectors and we need to do some operation with them. So first of all, we need to construct the u plus v. We do this by adding all the corresponding components. It's going to be 2, 1, 0, and 2. 2u plus minus v is obtained by multiplying all the components of the first vector to the 2 and then subtracting all the components of the second vector from this. It's going to be 0, 2, minus 2, and 4, minus 2, 0, 1, 0. So this is going to be minus 2, 2, minus 3, and 4. At the end, we just need to multiply these 2 vectors as a scalar multiplication. This is done by multiplying every corresponding component and adding all of them. It's going to be minus 4 plus 2 plus 0 plus 8, which is going to be equal to 6. In the second problem, we're given 2 vectors. We need to find the values for the lambda and omega and the mu, so that these 2 vectors are parallel. The 2 vectors v and omega are parallel if we can obtain the second vector by multiplying some constant to the first vector. So we see from here that lambda should be equal to the 2 and mu should be equal to the 1. In this case, these 2 vectors are becoming parallel because v becomes 2, 1, 2, and 2, and omega becomes 1, 1 over 2, 1, and 1, and we can obtain the v by multiplying the omega to the 2. In the question number 3, we need to find the determinant of the 2 P transpose Q inverse. We can split this to the multiplication of the 3 determinants of the 3 matrices. So it's going to be determinant of the 2 multiplied to the identity matrix with the same size, 4 by 4, multiplied to the determinant of the P transposed, multiplied to the determinant of the Q inverse. So this is going to be the determinant of the 2i. It's going to be 2 in the power of 4 because 2i is the identity matrix or similar to the identity matrix. His diagonal entries are equal to the 2 and his determinant is equal to the 2 in the power of 4. Multiplied to the determinant of the P transpose is 5. Multiplied to the determinant of the Q inverse is 1 over 4. So this is going to be 4 multiplied to the 5 is equal to the 20. In the question number 4, we need to find the multiplication of the eigenvalues of this matrix, which is going to be equal to the determinant of this matrix. So we need to find the determinant of this 4 by 4 matrix, and we're going to do this by going through the last row, for example. So we need to multiply the 2 to its cofactor, which is going to be 3, 4, plus 3 multiplied to its cofactor, which is c, 4, 4. So let's find the cofactor c, 3, 4, which is going to be minus 1 in the power of 3 plus 4 multiplied to the determinant of the matrix, which is obtained by eliminating the fourth column. Sorry, it should be 4, 3, fourth row, and third column. So which is going to be 1, 2, 4, minus 1, minus 2, minus 4, 2, 0, 3. So obviously the determinant of this matrix is equal to the 0 since this column, the first row and the second row are dependent. So if a matrix has 2 dependent rows, then determinant is equal to the 0. So now let's find the cofactor c, 4, 4, which is going to be minus 1 in the power of 4 plus 4, multiplied to the determinant, which is obtained by eliminating the last row and the last column. So which is going to be 1, 2, 2, minus 1, minus 2, 0, 2, 0, 6. And we can find its determinant by going through the last row again. So which is going to be 2 multiplied to the determinant of the matrix, 2, 2, minus 2, and 0, plus 6 multiplied to the determinant of the matrix, which is 1, 2, minus 1, minus 2. So please note I'm multiplying the 2 and 1 to the 1 since the position of the 2 is 3, 1 and the sum is even number. Position of the 6 is 3 and 3 and the sum is also an even number. So determinant of the second matrix is equal to the 0 again, because these two rows are dependent, and we can check this from the formula, right? So 1 multiplied to the minus 2 is minus 2. 1 multiplied to the minus 2 is also minus 2. If we subtract them, this is going to be equal to the 0. Determinant of the first matrix is equal to the plus 4. So which is going to be 2 multiplied to the 4, which is 8. We're going to substitute this 2 here, which is going to be 3 multiplied to the 8, which is 24. Now let's go through the questions and the problems from the second part. In the first problem, we need to find the diagonalization of this matrix. In order to do this, we need to first of all find the eigenvalues of this matrix. The sum of the eigenvalues is equal to the trace of this matrix, which is the sum of the entries on the main diagonal, which is going to be equal to the 3. And the multiplication of the eigenvalues is equal to the determinant of this matrix, which is going to be minus 10 plus 12, which is equal to the 2. So from here, it's obvious that the first eigenvalue is equal to the 2, and the second one is equal to the 1. Now we need to find its eigenvectors. So in order to do this, we are going to subtract the eigenvalues from the diagonal entries of this matrix. So basically A minus lambda 1 multiplied to the identity, which is going to be minus 2, 12, minus 1, and 5, minus 2, 0, 0, 2. If we do this, we're going to obtain the matrix minus 4, 12, minus 1, and 3. So we need to find the special solution for this matrix. In order to do this, we're going to bring this to the row echelon form by multiplying the first row to the minus 1 over 4 and adding this to the second. We're going to obtain the matrix minus 4, 12, 0, and 0. The second column is a free column, so that's why we set this to be equal to the 1. And we solve the first equation, which is minus 4 multiplied to the x1 plus 12 multiplied to the x2 is equal to the 0. If we substitute the x2 to be equal to the 1 to the second equation, we obtain that x1 should be equal to the 3. So basically, if you substitute the 3 and 1 for the x1 and x2 on this equation, we will get exactly 0. So the first eigenvector is going to be equal to 3 and 1. In order to obtain the second eigenvector, we're going to do the similar procedures. So now we're going to subtract the second eigenvalue, which is 1, from the diagonal entries of this matrix, which is going to be minus 3, 12, minus 1, and 4. Again, we bring this matrix to the row echelon form by multiplying the first row to the minus 1 over 3 and add this to the second. We bring this matrix to the row echelon form. Again, the second variable is the free variable. We set this to be equal to the 1 minus 3x1 plus 12xt is equal to the 0. From here, we obtain that x1 should be equal to the 4. So the second eigenvector is equal to 4 and 1. So this matrix lambda is obtained so we can construct this matrix lambda by putting the eigenvalues of this matrix on the diagonal matrix. It's going to be 2, 1, 0, 0. So this T matrices S and S inverse contains the eigenvectors of this matrix as the columns. So basically S matrix is going to be the first eigenvector and the second eigenvector, which is going to be 3, 1, 4, 1. So now we need to find the inverse of this matrix. We're going to do this using the cofactors method. So this is going to be 1 over determinant of this matrix S. Multiply the cofactor matrix and its transposed. So please note that determinant of this matrix S is going to be equal to the 3 minus 4, which is equal to the minus 1. So this is going to be minus 1 multiplied to the matrix, which is obtained by constructing all the cofactors C11, C12, C21, C22 transposed, which is going to be minus. So the C11 here is equal to the 1, C12 is minus 1, C21 is minus 4, and C22 is equal to the 3. We transpose this and multiply everything to the minus 1, and we obtain minus 1 and 1, 4 and minus 3. which is going to be the inverse of this matrix S. So now we can write down the A in the power of 4 as S lambda in the power of 4 multiplied to the S inverse. S in our case is going to be 3, 1, 4, 1. Lambda in the power of 4 is simply its diagonal entries in the power of 4. Basically 2 in the power of 4 is 16, 0, 0, and 1 in the power of 4 is still 1. Multiplied to the S inverse, which is going to be minus 1, 4, 1, minus 3. So if you multiply the three matrices, we're going to obtain minus 44, 180, minus 15, and 61. Let's go through the solutions for the second problem. We're given the matrix, we need to find its SVD decomposition. So it's clear that we need to start from the multiplication of the A transpose to the A, which is going to be 3, 2, 2, 2, 3, minus 2, multiplied to the A, which is 3, 2, 2, 2, 3, minus 2. If we multiply the first row to the first column, we obtain 9 plus 4 plus 4, which is 17. 3 multiplied to the 2 is 6, 2 multiplied to the 3 is 6, 2 multiplied to the minus 2 is 4. It's going to be 12 minus 4 is 8. Here we get 8 and 17 again. So we need to find its eigenvalues. The multiplication of its eigenvalues should be equal to the determinant, which is 17 and a square, minus 8 and a square, which is going to be 17 minus 8 multiplied to the 17 plus 8, which is going to be 9 multiplied to the 25. So this multiplication of the eigenvalues is equal to the, the sum of the eigenvalues is equal to the 34. So from here it's clear that the eigenvalues are 25 and 9. So the first eigenvalue is equal to the 25, then the second eigenvalue is equal to the 9. The sigma 1 and sigma 2, which are the singular values, are the square roots of the eigenvalues of this matrix, which are going to be 5 and 3. So in the second step, we need to find the orthonormal eigenvectors of this matrix, V1 and V2. In order to do this, from this matrix, we're going to subtract the lambda 1 and lambda 2 from the diagonal entries of this matrix. It's going to be A transpose to the A minus lambda 1 I. So basically, from the diagonal entries of this matrix, we need to subtract 25 first and then 9. If we subtract the 25, we're going to get minus 8, 8, 8, minus 8. If we bring this matrix to the row echelon form, it's going to be 8, 8, 0, and 0. So it's clear that the first eigenvector is equal to 1 and 1, since if we add the two columns of this matrix, right, if we multiply the first column to the 1 and second column to the 1, we obtain exactly 0 and 0. And the first orthonormal unit eigenvector is going to be 1 over square root of t and 1 over square root of t. The square root of 2 is coming from the lengths of this vector. So the A transposed multiplied to the A minus lambda 2 identity is equal to, if we subtract now 9 from the diagonal entries of this matrix, basically 9 from the 17s, it's going to be 8, 8, 8, and 8. So if we bring this matrix to the row echelon form, it's going to be 8, 8, 0, 0. So x2, the second eigenvector, is going to be minus 1 and 1. Since we multiply the first column to the minus 1 and the second column to the 1 and add them, we will get the 0, 0 column vector. V2 is going to be the unit vector with the same direction as this one. It's going to be minus 1 over square root of t, 1 over square root of t. So in the last step, C step, we need to find the U1 and U2. So we obtain the U1 by multiplying the A to the x1 and normalizing them. So if we multiply the A to the x1, so the A matrix was 3, 2, 2, 2, 3, minus 2. If we multiply this to x1, which is 1 and 1, so this is just a summation of these two columns. It's going to be 5, 5, and 0. So the unit vector in the same direction of this one, which is the U1, is going to be 1 over square root of t, 1 over square root of t, and 0. So the U2 is coming from of the multiplication of the A to the x2. 3 to 2 to 3 minus 2. We need to multiply this to the minus 1 and 1. It means that we need to subtract the first column from the second one. It's going to be minus 1, 1, and minus 4. So the length of this vector, actually, it's going to be 1 in the square plus 1 in the minus 1 in the square plus 4 in the square, which is going to be square root of 18, or we can write this as a 3 multiplied as the square root of t. So the u2 is going to be the unit vector in the same direction as this one, which is going to be minus 1 divided to the 3 square root of t, 1 divided to the 3 square root of t, minus 4 divided to the 3 square root of t. So we've got all the ingredients of the SVD decomposition of this matrix. A can be written as the U sigma V transpose, where the U has the U1 and U2 as the columns. It's going to be 1 over square root of t, 1 over square root of t, and 0, which is U1, minus 1 over square root of 18, 1 over square root of 18, minus 4 over square root of 18, which is going to be u2, multiplied to the sigma matrix, which contains the sigma 1 and sigma 2 as the diagonal entries, which are going to be 5, 0, 0, 3, multiplied to the v1 transposed, or v transpose, sorry. It's going to be v1 comes as the first row, 1 over square root of t, 1 over square root of t, and v2 comes as the second row, minus 1 over square root of t and 1 over square root of t. The problem number 3 is about the QR decomposition and the least square problem. So in the first step, we need to find the QR decomposition of this matrix. Let's denote this as the M. So since we're going to denote the big A as the vector. So we denote the first column of this matrix as the small a, which is going to be 1, 1, and 1. Second column is going to be small b, which is going to be 0, 1, and 2. Then, in the first step, we're going to do the Schmidt step, or the Gram step, when we need to construct the two vectors, big A and big B, which are orthogonal to each other. So big A is going to be simply small a, which is 1, 1, and 1. Big B is going to be B minus A transpose to the B, divided to the A transpose to the A, multiplied to the A. So small b is going to be 0, 1, and 2. A transpose to the B, it means I just need to multiply these two vectors as a scalar multiplication, which is going to be 1 multiplied to the 0, 1 multiplied to the 1, 1 multiplied to the 2, and sum them, which is going to be 3. A transpose to the A means I multiplied every component of the A to itself and sum them. It is going to be 1 in the square plus 1 in the square in 1 in the square, which is going to be 3 again. We need to multiply the A to this, which is going to be 1, 1, and 1. So this is going to be 0 minus 1 is minus 1. 1 minus 1 it's 0. 2 minus 1 is 1. So the big B is going to be this vector. In that these two vectors are orthogonal to each other, because if you multiply them, you will get exactly 0. So the Q1, which is going to be the first column, is just a normalized version of this A, which is obtained by dividing the A to its norm, which is going to be 1 over square root of 3, 1 over square root of 3, and 1 over square root of 3. Q2, which is the second column of the Q matrix, is obtained by dividing the B to its norm. It's going to be minus 1 over square root of 2, 0, and 1 over square root of 2. So we obtain the two columns of the Q matrix. So A should be written as the QR. If we multiply both of the sides of this equation to the Q transpose from here and from here, we'll obtain the identity here, since the Q transpose to the Q is the identity. So the R can be obtained by multiplying the Q transpose to the A. So the Q transpose is 1 over square root of 3. And the second row is going to be minus 1 over square root of 2, 0, 1 over square root of 2, multiplied to the A. A matrix is given as a 1, 1, 1, 0, 1, 2. If we multiply the first row to the first column, it's going to be just the sum of the three components. It's going to be 3 over square root of 3. If we multiply the first row to the second column, it's going to be this multiplied to the 1, this multiplied to the 2, and the sum is going to be again 3 over square root of 3. If you multiply this row to the first column, it's going to be 0. This row multiplied to this column, it's going to be 2 over square root of 2. So this is the R matrix actually. So we've got the Q and R matrix now, so we can solve the least square problem. So in order to do this, we're given the system AX is equal to ZB. We're just going to substitute the A with the QR decomposition. It's going to be QRX is equal to ZB. We're going to get rid of the Q by multiplying the both of the sides to the Q transposed. It's going to be Rx is equal to the Q transposed to the B, since Q transposed to the Q is equal to the identity matrix. So the R is given as 3 square root of 3, 3 over square root of 3, 0, 2 over square root of 2, multiplied to the x as x1 and x2, is equal to the Q transposed multiplied to the B. So let's multiply the Q transposed to the B first of all. It's going to be 3 square root of 3, square root of 3, square root of 3. Sorry, it was 1 over square root of 3, 1 over square root of 3, 1 over square root of 3, minus 1 over square root of 2, 0, 1 over square root of 2. This is the Q transposed, multiplied to the B, which is 3, 4, and 1. So this is given in the description of the problem, 3, 4, and 1. So if we multiply, what we obtain is, so we just need to sum this in the first row. That's going to be 3 plus 4 plus 1. It's going to be 8 over square root of 3. The second row multiplied to this column is going to be 3 minus 3 plus 1 is going to be 2 over square root of 2 with the minus. So now we need to substitute this to here. It's going to be 8 over square root of 3 minus 2 over square root of 2. From the second equation, it's clear that 2 over square root of 2 multiplied as x2 should be equal to this one. It's clear that x2 is equal to the 1, was the minus 1. So now we need to substitute this to the first equation, which is 3 over square root of 3 multiplied as x1 minus 3 over square root of 3, right? Since this one multiplied as x2, which is equal to the minus 1, is going to be minus 3 over square root of 3 is equal to the 8 over square root of 3. If it goes to the right, it is going to be 11 over square root of 3. If we divide everything to the 3 over square root of 3, we obtain that x1 should be equal to the 11 over 3. So this is the solution for the least square problem, AX is equal to the B, when we are solving this using the QR decomposition of the A matrix. And the last problem, we need to find the orthonormal basis of this plane. In order to do this, first of all, we're going to find its basis. So in order to do this, we need to find the special solutions for the following system. We first of all are going to write down this equation as a system of linear equations in a matrix form, which is going to be 1, 2, and 3, 0, 0, 0, 0, 0, 0, multiplied to the x, y, and z is equal to 0, 0, 0. So the system has the two free columns. So this is the free column and this is the free column. It means that it is going to have the two special solutions, which is going to be the basis of the solution space, the null space, right? So which is clear that it is going to be the plane, right? So the two special solutions are going to give us a plane. So the two free variables are going to be y and z. In order to find the first special solution, we set them y and z to be equal to the 1 and 0. And we solve the first system, which is x plus 2y plus 3z is equal to the 0. If we substitute the y to be equal to the 1 and z to be equal to the 0, we obtain that x is equal to minus 2. So the first special solution is minus 2, 1, and 0. In order to find the second special solution, we set y to be equal to the 0, z to be equal to the 1, and solve the same system. X plus 2y plus 3z is equal to the 0. We obtain x is equal to the minus 3. So the second special solution is going to be minus 3, 0, and 1. So we've got these two special solutions, and the plane can be explained as a linear combination of these two columns. Basically, this is the basis of this plane. Minus 2, 1, 0, minus 3, 0, and 1. So in order to find the orthonormal basis, we just need to do the Gram-Schmidt algorithm to find the Q matrix from this M, which is going to contain the orthonormal basis, Q1 and Q2. So we are going to do first of all the grams step. So this is the small a vector, this is small b vector. The big A vector is going to be minus 2, 1, and 0. Big B vector is going to be B minus A transpose as a B divided as A transpose A multiplied as A, which is minus 3, 0, 1, minus A transpose as a B means we just need to multiply these two vectors. It's going to be plus 6 plus 0, which is simply 6. So A transpose as A is going to be minus 2 multiplied to the minus 2, it's 4, plus 1, it's going to be 5, multiplied to the a, which is minus 2, 1, and 0. If I subtract these two vectors, it's going to be minus 3 over 5, minus 6 over 5, and 1. So these two vectors are orthogonal vectors. Since we multiply them, this is going to be equal to the 0. Let's multiply. Minus 2 multiplied to the minus 3 over 5, it's going to be 6 over 5. 1 multiplied to the minus 6 over 5, it's going to be minus 6 over 5. 0 multiplied to the 1 is 0, which is going to be equal to the 0. So now we need to get the orthonormal vectors. In order to do this, we just need to normalize these two vectors. The first vector, q1, is going to be a divided to the norm of the a, which is going to be minus 2 divided to the square root of 5, 1 over square root of 5, and 0. Q2 is going to be, this vector divided to its norm is going to be minus 3 over square root of 70, 6 minus 6 over square root of 70, and 1 divided to the square root of 70. So these two vectors are the orthonormal basis of that plane.